Welcome back to the deep dive. Today, we're taking a shortcut, maybe the ultimate shortcut, into the world of cryogenic fuels.
Yeah, specifically liquefied natural gas, LNG.
Exactly, LNG. It's become this really crucial transitional fuel for global shipping, hasn't it? Helping the industry move away from that old polluting heavy fuel oil, HFO.
It really has.
Mhm.
But here's the kicker. When you're dealing with something this valuable, this temperature sensitive and frankly volatile, how you calculate its energy content, that becomes everything. It's the difference between, smooth sailing financially and hitting some massive commercial rocks.
So that's our mission today, right? We're not just listing definitions.
No, definitely not. We need to unpack let's say the hidden complexities in LNG accounting. Getting the energy calculation precise isn't just about operational efficiency or planning how much fuel you need.
It's more fundamental.
It's the absolute bedrock for regulatory compliance. And in today's maritime world, that compliance basically decides if your ship can even operate legally.
The stakes are just incredibly high now, aren't they? Mostly because of the regulators. We should probably name them.
We have to. It all falls under the MARPOL Annex 6 framework. But the real teeth, the drivers forcing this precision, are the Energy Efficiency Existing Ship Index.
That's the EEXI.
Right, EEEX. And then its operational counterpart, the Carbon Intensity Indicator.
The CII.
That's the one. EEXI is more like a one-time technical hurdle for older ships. But the CII, that's the game changer.
Because it's ongoing.
Exactly. It's like an annual report card for the ship's carbon intensity. It forces operators to constantly track, prove, and improve their efficiency year after year.
And you can't calculate that intensity
without rigorous, verifiable accounting of the energy in the fuel you actually burned. Get the math wrong, you fail your CII grade. And that has huge knock-on effects in the market. Charterers won't touch a failing ship.
Okay, let's unpack this then. If compliance needs mathematical proof, we have to start right at the beginning. The basic ways energy is measured. LHV versus HHV.
Yes. And this, honestly, is where a surprising amount of confusion and, frankly, commercial risk still exists.
Yeah.
First, you've got the higher heating value, HHV.
Also called gross calorific value.
Right. That's the total theoretical energy released if you burn the fuel completely and you condense the water vapor produced back into liquid water. It captures that extra bit of heat, the latent heat.
Big but. Marine engines don't do that, do they? They just vent the water vapor straight out the exhaust stack as steam.
Precisely. They don't capture that latent heat. So that brings us to the lower heating value, LHV, or net calorific value.
Okay.
LHV excludes that latent heat of vaporization. It reflects only the usable energy that the engine can actually convert into power.
And that's the number that matters for performance.
Absolutely. Yeah. Engine performance specs, efficiency ratings, the official fuel consumption metrics, they're always based on LHV. So using HHV where LHV should be used, that's a massive commercial pitfall.
How big are we talking?
You end up overestimating the available energy by typically 10 to 11%.
Hold on. 10 to 11%. On a multi-million-dollar bunker delivery, that's potentially hundreds of thousands of dollars just vanished on paper.
Exactly. Forget compliance for a second. Think about voyage planning. If you calculate your fuel needs based on that inflated HHV number,
you could literally run out of fuel, needing an expensive, maybe dangerous diversion.
It's a critical error baked right into the definition. And we haven't even touched on the fuel's quality variability yet.
Ah, right. Because LNG isn't just pure methane.
Not at all. It's primarily methane, sure, maybe 85% to sometimes up to 99%. Mm-hmm. But those other bits, the trace components like heavier hydrocarbons, ethane, propane, or even inert gases like nitrogen, they directly impact the fuel's density and its calorific value. Yes. Significantly.
So unlike, say, marine gas oil, which is fairly consistent, LNG is more like a recipe that changes slightly with each batch?
That's a good way to put it. The LHV can typically range anywhere from, say, 45 to 50 megajoules per kilogram. That's quite a spread.
And if you just use a generic average LHV number in your calculations?
You're introducing potentially substantial errors. Even if you correctly chose LHV over HHV, ignoring the actual composition of that specific batch leads to bad planning. You absolutely need to know the precise molecular breakdown of the fuel you just bought. It's non-negotiable for accuracy.
Okay, so we've established that the exact composition is critical for energy calculation and avoiding commercial risk. But there's another angle, isn't there? How does the operator ensure that the specific LNG they bought is actually compatible and, safe for their very expensive, high-tech, dual-fuel engine?
Right. Now we're shifting from accounting risk to operational and safety risk. This is where we need to talk about the methane number, or MN.
Methane number.
You can think of the methane number. Well, it's basically the natural gas equivalent of the octane rating you see for gasoline at the pump.
Ah, okay. So higher octane prevents engine knocking or pre-ignition in a car.
Exactly the same principle. The MN quantifies the gas fuel's resistance to knocking, which is uncontrolled, damaging combustion.
Yeah.
Pure methane has an MN of 100, very resistant.
But if you get those heavier hydrocarbons like ethane or propane in the mix,
The MN drops, sometimes sharply, and modern marine gas engines, especially the high-pressure ones like MEGI or low-pressure XDF, they have minimum MN requirements set by the manufacturer.
And if the fuel's MN is too low?
The engine's control system will detect the risk of knocking and automatically derate itself. It cuts power to prevent damage. That's an immediate operational hit, a direct consequence of poor fuel quality.
Okay, so MN protects the engine itself from knocking, but what about just ensuring stable, reliable burning once the gas is flowing? Does composition affect that too?
It does. And for that, we look at the Wobbe index, or WI.
Wobbe index, right. I've heard of that. We probably don't need the exact formula.
No, but operationally, the WI is super important. It's essentially an indicator of how interchangeable different fuel gases are for a given burner system. It helps predict if you'll get stable combustion.
So consistency again?
Yes. Engine and boiler manufacturers specify a fairly tight acceptable WI range, usually somewhere around 47 to 52 megajoules per normal cubic meter.
And if the fuel's WI falls outside that window,
You risk unstable combustion. That could mean flameouts, reduced efficiency, or uneven heating, which can damage equipment over time. It ensures the fuel performs predictably in the combustion chamber.
and logically, the only way to calculate all these critical numbers, LHV, MN, WI, relies on knowing that precise molecular breakdown we talked about earlier.
Absolutely, you need the exact recipe.
Is there a specific standard that mandates how you get that recipe?
There is. It's ISO 6976. That's the international standard. It dictates the methodology for calculating calorific values, density, Wobbe index, and other properties from the composition.
And how do you determine the composition?
ISO 6976 essentially mandates the use of gas chromatography, or GC analysis. It's not enough to estimate or use generic values. You have to use a GC to precisely separate and quantify every component down to the trace elements.
Because even tiny amounts matter.
That tiny bit of nitrogen or ethane significantly impacts the final calculated values. The GC analysis provides the verified compositional data that everything else LHV, MN, WI calculations relies upon. It's the foundation of proof.
Okay, so we've got the composition mapped for energy content, safety, and combustion stability. But knowing the recipe doesn't automatically tell you how much stuff you received. How do we bridge that gap? How do we ensure the mass, the actual quantity of energy paid for, is what ended up in the ship's tanks?
Now we're talking custody transfer. High-stakes stuff, making sure the buyer gets what they paid for.
And the key here is measurement technology.
It's paramount. The undisputed gold standard for LNG custody transfer is using Coriolis flow meters. These are mass metering devices
Why are they preferred?
because they measure the mass flowing through them directly. They're largely independent of the fluid's temperature, pressure, or density, all of which fluctuate wildly with LNG. This dramatically minimizes measurement uncertainty compared to other methods.
So mass metering solves it. Pay for mass, measure mass, job done.
Mostly. For the flow measurement itself, yes, but volume measurements are still common, especially for checking tank levels before and after bunkering. And if volume is used as part of the custody transfer calculation,
It needs correcting.
rigorously temperature compensated, yes.
Yeah.
But here's another, perhaps more subtle, commercial risk, even lurking sometimes with mass metering data, depending on how things are calculated: density determination.
Ah, density. Sounds
Yeah.
simple, but I'm guessing with LNG it's complicated.
Extremely. LNG density varies significantly, maybe from 430 to 470 kilograms per cubic meter. And it's incredibly sensitive to both temperature and the precise composition we just discussed.
So where's the pitfall?
The huge commercial error happens if one party in the transfer, maybe the supplier or even the ship based on shore figures, uses a fixed, generic, or outdated density value in their calculations instead of using sophisticated composition-based calculation models.
Like specific software.
Exactly. The industry standard is the GRRG 2008 equation of state, or similar validated models. These take the real-time temperature and the actual GC composition data to calculate the density accurately at the transfer conditions.
So if you just use a single average density number,
Your calculation of mass from volume, or even cross-checking mass meter readings against tank volumes, can be significantly off. If the temperature is just slightly different from what your generic density assumes, the mass calculation is wrong.
And if the mass is wrong, the total energy transferred calculation is wrong.
Precisely. It undermines the entire principle of fair trade for these very high-value fuel transactions.
Which loops back to the paperwork, doesn't it? The final bunker delivery note or certificate.
Absolutely. Bunkering procedures need to follow standards like those from GIIGNL, covering pre-bunkering checks, joint measurements, sampling, GC analysis. And that final certificate must clearly state the total mass and, crucially, the total energy transferred based on agreed calculation methods to prevent disputes later.
Documentation is the final seal on the deal.
Okay, let's shift gears slightly. We've covered measurement and calculation. What about just the day-to-day reality of having this ultra-cold fuel on board? There's an inherent challenge, right? This stuff is always boiling.
Always. That's boil-off gas, or BOG. It's unavoidable. Heat naturally leaks into the cryogenic tanks, however well insulated they are, and causes a small amount of the LNG to continuously vaporize.
And we measure this as the boil-off rate?
Correct, the BOR. In modern ships, it's typically quite low, maybe 0.05% to 0.15% of the tank volume per day. But you can't just vent this gas.
Safety and environmental rules forbid it. Methane is a potent greenhouse gas.
Exactly. So this creates an immediate operational puzzle for the ship's crew. What do you do with this constantly generated BOG?
Two options, basically. Burn it or reliquefy it.
That's it. The best option from an energy efficiency standpoint is utilization. Feed that BOG directly into the dual fuel main engines or auxiliary engines.
It's essentially free fuel you've already paid for. Precisely. Maximize its use. But what if the ship is at anchor or maneuvering at low speed and the engines don't need all the gas being produced?
Then you have surplus BOG.
And that's where reliquefaction comes in. Onboard plants can capture this excess BOG and condense it back into liquid LNG in the tanks.
Sounds like a neat solution. Prevents emissions.
It does, but it comes at a cost, a significant energy cost.
The compressors and cooling systems for the reliquefaction plant consume power.
A lot of power. And this compressor energy penalty absolutely must be factored into the ship's overall energy balance and efficiency calculations.
Especially for the CII rating.
Definitely. Running the reliquefaction plant reduces the ship's net efficiency. You have to account for that energy consumption accurately.
Oh.
Ignoring it would artificially inflate your efficiency metrics.
So fuel planning suddenly gets even more complex. You're not just calculating consumption, you're forecasting BOG generation, how much you can utilize, how much you'll likely have to reliquefy, and the energy cost of doing so.
It's a real tightrope walk. And that's why ships need substantial operational margins in their fuel planning.
How much margin are we talking?
It varies, but 5% to maybe even 15% of the planned voyage consumption isn't unusual. You need buffer for, well, minimum liquid levels required in the tanks for pump operation, the so-called heel. You need it for uncertainty in BOG rates, which can fluctuate.
And getting the BOG projection wrong
can lead to unnecessarily high costs from running the reliquefaction plant more than needed, or far worse, miscalculating your usable fuel and running short.
Right. We've covered a lot of ground here. LHV, HHV errors, the importance of methane number for safety, Wobbe index for combustion, density modeling traps, Coriolis meters, BOG management penalties. If we tie all these threads together, what's the big picture takeaway for, say, a shipping executive trying to navigate this?
The big picture. It's that precise, verified energy calculation isn't a nice to have anymore. It is the fundamental underpinning of both regulatory survival and commercial success in the LNG era.
Survival because of EEXI and CII?
And the upcoming Fuel EU maritime regulation in Europe, which will add more greenhouse gas intensity rules. Proving compliance demands accurate energy accounting.
And commercial success.
Because the market runs on energy equivalence.
Yeah.
Charter agreements, fuel purchasing decisions, comparing LNG against other fuels. It all relies on converting prices to a common energy basis, usually dollars per gigajoule, 2J. If your energy calculation is flawed, your commercial decisions, your pricing, your competitiveness, it's all built on shaky ground. You can't accurately price your service or prove your environmental performance to increasingly demanding stakeholders and financiers.
Looking ahead now, the industry isn't stopping at fossil LNG, is it? We're already hearing a lot about Bio-LNG.
Which is liquefied biomethane, essentially.
And also synthetic methane or E-Methane.
Right, made using renewable energy and captured carbon. These are really exciting because they're essentially drop-in fuels.
Meaning they can use the same engines, the same tanks, the same bunkering infrastructure as fossil LNG.
Exactly. They offer a pathway to much deeper decarbonization without needing entirely new ship designs or massive infrastructure overhauls immediately.
Mm-hmm.
But, And here's the thought I want to leave you with, something to really chew on.
Okay.
While these green methanes solve the source problem, potentially, they rely on the exact same rigorous ISO 6976 calculation standards for their energy content that we've just spent all this time discussing.
So the measurement challenge remains identical.
Identical for the energy part. But the future challenge becomes twofold. First, you still need that precise real-time compositional analysis and energy calculation for every single batch, because Bio-LNG and synthetic methane can also have compositional variations.
And the second part?
The second, and arguably harder part, will be robustly verifying the renewable origin of that fuel, proving it's genuinely bio or synthetic to satisfy regulators and justify the green premium it will inevitably command. That need for sophisticated, trustworthy analysis, both compositional and origin tracking, is only going to get more intense. The math and the verification